Right now, as you move through the world around you, you're navigating through exactly 3 dimensions of space: forward and backward, left and right, up and down. This seems so natural, so obvious that we rarely question why space works this way. But this apparent simplicity masks one of the deepest mysteries in physics. Why does our universe contain precisely 3 spatial dimensions instead of 2, 4, 5, or even infinite dimensions? The question isn't merely academic. In a universe with just 2 spatial dimensions, complex chemistry would be impossible, stars couldn't form, and life as we know it could never exist. In a universe with 4 or more spatial dimensions, atoms would be unstable. Gravity would behave so differently that planets couldn't maintain stable orbits, and the very concept of solid matter might cease to have meaning. Consider what makes our 3-dimensional world possible. Every breath you take depends on molecules navigating through 3-dimensional space to reach your lungs. Every heartbeat relies on blood flowing through 3-dimensional networks of vessels. Every thought in your brain depends on electrical signals traveling through 3-dimensional neural networks. The dimensionality of space isn't just a mathematical abstraction. It's the fundamental framework that makes complexity, structure, and ultimately, life possible. But mathematics tells us that spaces with any number of dimensions are perfectly consistent logical possibilities. We can write equations describing 2-dimensional flatlands, 4-dimensional hyperspace, or even spaces with infinite dimensions. Computer simulations can model worlds with different numbers of dimensions. Yet somehow, our universe selected exactly 3 spatial dimensions from this infinite menu of mathematical possibilities. The mystery deepens when we realize that our best theories of fundamental physics suggest space might actually contain more than 3 dimensions. Dimensions so small and curled up that we can't detect them directly. String theory, our most promising candidate for a theory of quantum gravity, requires space to have at least 6 additional dimensions beyond the 3 we experience. These extra dimensions might be real and present all around us, yet somehow hidden from our everyday experience. Dr. Lisa Randall at Harvard University has shown that extra dimensions could exist at scales as large as millimeters, influencing gravity in ways we haven't yet detected. If such dimensions exist, why do we experience only 3? What determines which dimensions remain large and accessible while others shrink to invisibility? The question of dimensional ITY connects to the deepest problems in modern physics. Why do the fundamental forces have the relative strengths they do? Why do particles have the masses we observe? Why does the universe contain the right balance of matter and energy to allow complex structures to form? The answers to all these questions might trace back to the fundamental reason why space has exactly 3 large dimensions. Throughout human history, our understanding of space has evolved dramatically. Ancient civilizations conceived of space as the stage where earthly and celestial events unfolded. Newton imagined absolute space as a fixed background against which motion occurred. Einstein revealed that space and time form a unified 4-dimensional spacetime that curves under the influence of matter and energy. Now, modern physics suggests that space might be far stranger than Einstein imagined. The Standard Model of particle physics describes all known matter and forces using quantum field theory in 3 spatial dimensions plus time. Yet this highly successful theory cannot explain why space has 3 dimensions rather than some other number. The theory works brilliantly within 3-dimensional space, but it doesn't explain why that space exists in the first place. Cosmological observations reveal that our universe began in a hot, dense state approximately 13.8 billion years ago and has been expanding ever since. But did the dimensionality of space emerge during this cosmic evolution, or was it somehow selected during the universe's first moments? Understanding why space has 3 dimensions might require understanding how the universe itself came into existence. The anthropic principle provides one perspective on cosmic dimensionality. Perhaps we observe three spatial dimensions simply because universes with different numbers of dimensions cannot support observers like ourselves. If most possible universes have numbers of dimensions incompatible with complex chemistry and stable structures, then conscious observers would inevitably find themselves in universes like ours. Yet this anthropic reasoning feels unsatisfying to many physicists. It suggests that the dimensionality of space is determined by the requirement for observers rather than by fundamental physical principles. A more complete understanding would explain why three-dimensional space emerges naturally from the basic laws of physics. String theory offers the most developed framework for understanding why space might have more than three dimensions. In string theory, fundamental particles are endpoint objects, but tiny vibrating strings moving through a space with at least 10 dimensions. The different vibrational patterns of these strings correspond to the different particles we observe, while the geometry of the extra dimensions determines the properties of those particles. But string theory faces its own dimensional puzzle. If space contains 6 or 7 extra dimensions beyond the 3 we experience, why are those extra dimensions small and hidden rather than large and obvious? This compactification problem requires understanding what physical processes could cause some spatial dimensions to remain large while others shrink to subatomic scales. If you're fascinated by fundamental questions about reality and the deepest mysteries of physics, subscribe and hit thumbs up. And here's something to ponder. If you could somehow experience four-dimensional space directly, what would that feel like? Comment your thoughts below. I'll pin the most creative visualization. Tonight, we're going to explore how the dimensionality of space determines everything from the stability of atoms to the possibility of life itself. We'll discover how different numbers of dimensions would create universes with physics so alien that nothing resembling our world could exist. We'll uncover how modern physics suggests space might be far more complex than our three-dimensional experience suggests. This isn't just abstract mathematical speculation. Understanding dimensional IT could be key to developing a theory of quantum gravity, explaining dark energy and dark matter, and potentially even enabling technologies that seem like science fiction today. The number of spatial dimensions represents one of the most fundamental properties of reality. Every step you take, every object you manipulate, every geometric relationship you perceive depends on space having exactly 3 dimensions. Yet this seemingly obvious fact emerges from physics so subtle and profound that we're only beginning to understand why 3-dimensional space exists, rather than any other possibility. Now let's begin our journey into the heart of dimensional reality, where we'll discover how the structure of space itself determines what's possible in our universe. Chapter 1. Dimensional Basics. Understanding why space has 3 dimensions requires first grasping what we mean by dimension and how different numbers of dimensions would fundamentally alter the nature of reality itself. A dimension represents an independent direction of movement through space, a degree of freedom that allows you to change your position in ways that cannot be achieved by moving along other dimensional directions. The concept seems simple until you realize that the number of dimensions determines nearly everything about how physics works. In one-dimensional space, movement is restricted to a single line. You can only move forward or backward along this line, with no possibility of stepping aside, turning, or exploring any other direction. Such a universe would be impossibly constraining. Imagine trying to navigate around an obstacle when you can only move along a single direction. Complex structures, chemistry, or life would be fundamentally impossible in such a linear world. Two-dimensional space adds perpendicular movement to create a flat plane where objects can move forward backward and left-right, but not up-down. This flatland universe would be richer than one-dimensional space, but still severely limited. While simple geometric shapes could exist, three-dimensional structures like molecules, cells, or any complex mechanical systems would be impossible. The mathematics of two-dimensional space allows for interesting geometry, but the physics becomes problematic for complex structures. Dr. Edwin Abbott's 1884 novel, Flatland, explored the conceptual challenges of two-dimensional existence, imagining how creatures confined to a plane might perceive three-dimensional objects passing through their world. A sphere moving through Flatland would appear as a circle that mysteriously changes size, demonstrating how dimensional limitations constrain not only movement, but perception and understanding. Three-dimensional space provides the freedom to move in three mutually perpendicular directions: forward, backward, left, right, and up, down. This creates the familiar world we experience, where complex structures can form, objects can move around obstacles, and intricate geometrical relationships become possible. The richness of three-dimensional space enables everything from molecular chemistry to architectural engineering. Four-dimensional space would add another perpendicular direction, impossible to visualize directly because our brains evolved in three-dimensional environments. Mathematically, we can describe four-dimensional space using coordinate systems with four independent variables, but geometric intuition breaks down. Objects in four-dimensional space could move in ways that seem magical to three-dimensional beings. Imagine being able to step outside ordinary space to move around obstacles or reach inside closed containers. The mathematical framework for understanding arbitrary numbers of dimensions comes from linear algebra and differential geometry. An n-dimensional space requires n independent coordinates to specify any location uniquely. The distance between 2 points involves a generalization of the Pythagorean theorem to n dimensions, while geometric objects like lines, planes, and higher dimensional surfaces follow well-defined mathematical rules. Vector spaces provide the mathematical foundation for understanding dimensional spaces. In an undimensional vector space, any point can be represented as a linear combination of n basis vectors that point along independent directions. The dimension of the space equals the minimum number of basis vectors needed to reach any point in that space through linear combinations. Degrees of freedom represent another way to think about dimensionality. Each dimension provides 1 degree of freedom for movement or configuration. A point in three-dimensional space has 3 translational degrees of freedom. A rigid object adds 3 rotational degrees of freedom for 6 total. The number of dimensions available fundamentally limits the complexity of possible motions and configurations. The concept of dimensionality extends beyond spatial geometry to include abstract mathematical spaces. The space of all possible quantum mechanical states for a system can have infinite dimensions. The space of all possible solutions to a differential equation might require many dimensions to characterize completely. Physical space represents just one type of dimensional structure among many mathematical possibilities. Topology studies properties of spaces that remain unchanged under continuous deformations. A sphere and an ellipsoid have the same topological properties despite different geometric shapes, while a sphere and a torus differ topologically. The topological structure of space can be more fundamental than its geometric properties in determining what kinds of physics are possible. Manifolds provide the mathematical framework for describing spaces that locally look like familiar flat space but might have different global structure. Earth's surface is a two-dimensional manifold embedded in three-dimensional space, locally flat like a plane, but globally curved like a sphere. Higher dimensional manifolds can have much more complex structures that are difficult to visualize but mathematically well-defined. The dimensionality of space affects how volumes scale with size. In 3 dimensions, volume scales as length cubed. Doubling all linear dimensions increases volume by a factor of 8. In n dimensions, volume scales as length to the nth power. This scaling relationship has profound implications for physics, affecting everything from atomic structure to gravitational dynamics. Surface area scaling also depends on dimensionality in ways that affect physical processes. In 3 dimensions, surface area scales as length squared, creating the familiar square-cube law that limits the size of biological organisms and engineering structures. Different dimensional spaces would have different scaling relationships with dramatically different consequences for possible structures. The mathematical consistency of spaces with arbitrary numbers of dimensions raises the question of why physical space should have any particular number of dimensions. Mathematics alone cannot determine the dimensionality of physical space. This must come from physics, cosmology, or perhaps anthropic reasoning about what dimensions are compatible with observers. Coordinate systems provide practical methods for describing positions and motion in spaces of different dimensions. Cartesian coordinates use perpendicular axes, while spherical coordinates use radial distance and angles. The choice of coordinate system affects how mathematical expressions look, but doesn't change the underlying physics or geometry. Dimensional analysis represents a powerful tool for understanding physical relationships that depends critically on the dimensionality of space. Physical quantities have dimensions like length, time, and mass that must balance in any valid physical equation. The specific values of fundamental constants depend on both the units chosen and the number of spatial dimensions. The visualization of higher dimensional spaces challenges human intuition, but can be approached through various techniques. Cross-sections reveal how higher dimensional objects appear when intersected by lower dimensional spaces. Projections show shadow-like representations of higher dimensional objects in lower dimensional spaces. Mathematical visualization tools enable exploration of geometric relationships in arbitrary numbers of dimensions. Symmetries play crucial roles in determining how physics works in spaces with different numbers of dimensions. Rotational symmetries become richer in higher dimensions. 3-dimensional space allows rotation around axes, while 4-dimensional space allows rotation around planes. These symmetries affect conservation laws and physical interactions in fundamental ways. The relationship between local and global properties of space becomes more complex in higher dimensions. Spaces that look locally 3-dimensional might have global structure requiring additional dimensions to describe properly. Einstein's general relativity describes space-time as a 4-dimensional manifold that curves under the influence of matter and energy. Understanding dimensional basics provides the foundation for exploring how different numbers of dimensions would affect fundamental physics. The mathematical consistency of higher dimensional spaces contrasts sharply with the apparent uniqueness of 3-dimensional space in our universe. This tension between mathematical possibility and physical reality drives much of modern theoretical physics. The study of dimensional spaces also reveals deep connections between geometry and physics that were unapparent when these subjects developed separately. Modern physics increasingly relies on geometric concepts, while geometry gains physical meaning through applications to fundamental theories like general relativity and quantum field theory. As we'll discover next, the apparently simple question of spatial dimensionality becomes far more complex when we consider how different numbers of dimensions would affect the fundamental forces that govern atomic structure, chemistry, and the possibility of stable matter. Chapter 2. Physics in Different Dimensions. The number of spatial dimensions fundamentally determines how every physical force and interaction operates, creating universes where the basic laws of physics would be so alien that nothing resembling our world could exist. Understanding how forces behave in different dimensional spaces reveals why 3-dimensional space seems uniquely suited for complex structures, stable matter, and ultimately, life itself. Gravity represents the most dramatically dimension-dependent force, with its strength and behavior changing radically as the number of spatial dimensions varies. In our 3-dimensional universe, gravitational force follows Newton's inverse square law. Doubling the distance between two masses reduces gravitational attraction by a factor of 4. This familiar relationship emerges directly from three-dimensional geometry. In two-dimensional space, gravitational force would follow an inverse first-power law. Doubling distance would only have gravitational attraction rather than quartering it. This stronger fall-off might seem beneficial, but it creates insurmountable problems for orbital mechanics. Planetary orbits in two-dimensional space would be fundamentally unstable, with planets either spiraling into their stars or escaping to infinity with no possibility of stable circular or elliptical trajectories. Dr. Paul Ehrenfest first analyzed orbital stability in spaces with different numbers of dimensions in 1917, showing that stable closed orbits require exactly 3 spatial dimensions. In 2 dimensions, orbits are unstable. In 4 or more dimensions, gravitational attraction falls off so rapidly with distance that bound orbits become impossible except under very special circumstances. 4-dimensional space would create an inverse cube law for gravity, where doubling distance reduces gravitational force by a factor of 8. This extremely rapid falloff would prevent planetary systems from forming and maintaining stable configurations over astronomical timescales. Even if planets somehow formed, their orbits would decay rapidly due to perturbations that would be easily amplified in such a steep gravitational potential. The mathematics underlying these dimensional effects comes from Gauss's law, which relates the strength of fields to the geometry of surrounding space. In n-spatial dimensions, gravitational and electrical field strengths fall off as 1 Rn1, where R represents distance. This relationship directly connects spatial geometry to fundamental force laws. Electromagnetic forces would also behave dramatically differently in spaces with other numbers of dimensions. The Coulomb force between electric charges follows the same dimensional scaling as gravity. Inverse square law in 3 dimensions, inverse first power in 2 dimensions, inverse cube in 4 dimensions. These changes would fundamentally alter atomic structure and chemical bonding. Atomic stability depends critically on the balance between electromagnetic attraction and quantum mechanical effects that emerge from wave-like properties of electrons. In 2-dimensional space, this balance would shift in ways that make stable atoms impossible. Electrons would be pulled too strongly toward atomic nuclei, eliminating the quantum mechanical structure that creates distinct energy levels and electron shells. In 4-dimensional space, electromagnetic attraction would weaken so rapidly with distance that electrons could not be bound effectively to nuclei except at very short ranges. This would create atoms with radically different properties, either much smaller and more tightly bound, or too weakly bound to maintain stable chemical configurations. The quantum mechanical description of atoms involves solving Schrödinger's equation in whatever number of spatial dimensions exists. The mathematical solutions change dramatically with dimensionality, leading to different energy level structures, orbital shapes, and bonding properties. Only in 3-dimensional space do we get the familiar electron shells and chemical periodic table that enables complex chemistry. Dr. Freeman Dyson analyzed how atomic physics would work in spaces with different numbers of dimensions, showing that stable matter requires exactly 3 spatial dimensions. In fewer dimensions, atoms collapse. In more dimensions, atoms either don't bind or have such different properties that complex chemistry becomes impossible. Nuclear forces represent another category of interactions that depend on spatial dimensionality, though these short-range forces are less sensitive to dimensional effects than gravity and electromagnetism. However, the balance between nuclear attraction and electromagnetic repulsion in atomic nuclei would shift with dimensionality in ways that affect nuclear stability and radioactive decay. Fluid dynamics and thermodynamics would operate by completely different rules in spaces with different numbers of dimensions. The relationship between surface area and volume determines heat transfer rates, diffusion processes, and mechanical properties of materials. These scaling relationships would change with dimensionality in ways that affect everything from stellar structure to biological metabolism. Wave propagation follows different mathematical laws in different dimensional spaces. Sound waves, electromagnetic radiation, and quantum mechanical wave functions all propagate according to wave equations whose solutions depend critically on the number of spatial dimensions. Three-dimensional space provides unique properties for wave propagation that affect communication, energy transport, and quantum mechanical behavior. The inverse square law for electromagnetic radiation emerges from three-dimensional geometry. Light from a point source spreads over spherical surfaces whose area scales as distance squared. In 2 dimensions, light intensity would decrease more slowly with distance. In 4 dimensions, it would decrease more rapidly. These differences would dramatically affect how energy propagates through space. Phase transitions and critical phenomena in statistical mechanics depend on dimensionality in subtle but important ways. The behavior of materials near phase transition points follows scaling laws that change with the number of dimensions. Three-dimensional space provides specific critical exponents and universality classes that determine how matter behaves under extreme conditions. Topological properties of fields and particles become more complex in higher dimensions, potentially allowing for exotic structures like magnetic monopoles, topological solitons, and non-trivial vacuum configurations that might not exist in three-dimensional space. These exotic possibilities could fundamentally alter particle physics and cosmology. The strength of quantum fluctuations depends on dimensionality through the density of quantum states available at different energies. Higher dimensional spaces provide more quantum states, potentially making quantum effects more important. Lower dimensional spaces restrict quantum fluctuations in ways that could suppress interesting quantum phenomena. Symmetry groups become richer in higher dimensional spaces, providing more possible symmetries for physical laws. Three-dimensional space allows rotation groups, sulfur monoxide, 3, and Lorentz groups, while higher dimensions enable larger symmetry groups that could unify forces in different ways or allow for fundamentally different types of physical interactions. The mathematical structure of differential equations changes with dimensionality in ways that affect whether physical problems have stable, unique solutions. Some types of partial differential equations behave well in 3 dimensions, but become ill-posed in other numbers of dimensions, potentially making physics either too simple or too chaotic to support complex structures. Field theory in different dimensions involves different mathematical techniques and produces different types of solutions. Gauge theories, which describe fundamental forces, work differently in different numbers of dimensions. The Yang-Mills equations that describe non-abelian gauge theories have different properties and solution structures depending on spatial dimensionality. String theory suggests that fundamental physics might naturally operate in higher dimensional spaces, with our three-dimensional experience emerging from a higher dimensional reality through compactification or other mechanisms. Understanding how physics works in the full high-dimensional space might be necessary for understanding why we observe only 3 large dimensions. The renormalization group, which describes how physical theories change when observed at different energy scales, operates differently in different numbers of dimensions. Some theories that are well-behaved in 3 dimensions become non-renormalizable in 4 dimensions, while others require specific numbers of dimensions for mathematical consistency. Perhaps most remarkably, the analysis of physics in different dimensions reveals that 3-dimensional space occupies a unique position where complex structures can form and remain stable over long time periods. The specific balance of forces, quantum effects, and geometric relationships in 3 dimensions seems precisely tuned to allow the emergence of complexity, chemistry, and life. This dimensional fine-tuning raises profound questions about why our universe has exactly the number of dimensions that enables complex structures to exist. As we'll explore next, the mathematical frameworks that describe spaces with more than 3 dimensions reveal even deeper mysteries about the nature of reality. Chapter 3. Higher Dimensional Mathematics. The mathematical description of spaces with more than 3 dimensions opens doorways to geometric relationships and symmetries so rich and complex, they challenge our ability to visualize or even conceptualize reality beyond our everyday experience. Yet these mathematical frameworks provide the essential tools for understanding modern physics theories that propose our universe actually contains many more dimensions than we directly perceive. 4-dimensional space introduces mathematical concepts that have no direct analogs in lower dimensions. The 4-dimensional analog of a cube, called a tesseract or 8-cell, contains 16 vertices, 32 edges, 24 square faces, and 8 cubic cells. While impossible to visualize directly, the tesseract possesses mathematical properties and symmetries that extend familiar 3-dimensional relationships into new realms. Dr. Charles Howard Hinton pioneered the mathematical study of 4-dimensional geometry in the late 19th century, developing systematic methods for understanding higher dimensional shapes and their properties. Hinton's work revealed that 4-dimensional space contains rotations around planes rather than axes, fundamentally different from 3-dimensional rotations around lines. Rotation in 4-dimensional space involves 2 independent plane rotations that can occur simultaneously, without interfering with each other. This double rotation property has no analog in 3 dimensions and represents one example of how higher dimensional mathematics reveals phenomena impossible to experience directly, but perfectly well-defined mathematically. The mathematics of n-dimensional geometry relies on generalized concepts like hyperplanes, which represent un-1-dimensional surfaces within n-dimensional spaces. In 3 dimensions, hyperplanes are ordinary 2-dimensional planes. In 4 dimensions, hyperplanes are 3-dimensional spaces. These hyperplanes can intersect in complex ways that create rich geometric structures. Vector spaces provide the mathematical foundation for understanding arbitrary dimensions through linear algebra. An n-dimensional vector space requires n linearly independent basis vectors, and any vector in the space can be expressed as a unique linear combination of these basis vectors. The mathematical operations of addition, scalar multiplication, and inner products extend naturally to any number of dimensions. The dot product between vectors generalizes to arbitrary dimensions as the sum of products of corresponding components. This operation measures angles between vectors and enables the definition of orthogonality, perpendicularity, in any number of dimensions. Orthogonal transformations preserve angles and distances while rotating or reflecting vectors. Cross products, which create vectors perpendicular to 2 given vectors in 3 dimensions, generalize differently to higher dimensions. 4-dimensional space allows for wedge products that create bivectors representing oriented plane segments. 7-dimensional space permits cross products similar to 3 dimensions, but most other dimensions lack this specific structure. Matrix mathematics becomes increasingly important for higher dimensional analysis because matrices provide compact representations of linear transformations between vector spaces. Rotation matrices in n dimensions are n times n orthogonal matrices with determinant +1, and these matrices form groups with rich mathematical structure. The orthogonal group On consists of all distance-preserving linear transformations in n-dimensional space, while the special orthogonal group sulfur monoxide N includes only orientation-preserving transformations. These groups have different properties in different dimensions. For instance, SO4 is isomorphic to sulfur monoxide 3 times sulfur monoxide 3, a unique property not shared by other dimensions. Differential geometry extends calculus to curved spaces of arbitrary dimension through the mathematics of manifolds. A manifold is a space that locally resembles flat Euclidean space, but can have complex global structure. Earth's surface is a two-dimensional manifold embedded in three-dimensional space, while higher-dimensional manifolds can have incredibly complex geometric properties. Riemannian geometry describes how to measure distances, angles, and curvature in higher-dimensional curved spaces. The metric tensor provides a mathematical tool for calculating these geometric quantities, generalizing the Pythagorean theorem to curved spaces of any dimension. Einstein's general relativity uses Riemannian geometry in four-dimensional spacetime. Curvature in higher dimensions becomes increasingly complex, with different types of curvature measured by mathematical objects, like the Riemann curvature tensor. In two dimensions, curvature is characterized by a single number at each point. In four dimensions, the curvature tensor has 20 independent components, representing the much richer geometric possibilities. Fiber bundles represent mathematical structures where higher dimensional spaces are organized as families of lower dimensional spaces. A fiber bundle consists of a base space, a fiber space, and a projection that maps the total space onto the base space. These structures appear throughout modern physics in gauge theories and general relativity. Topology studies properties of spaces that remain unchanged under continuous deformations. Higher dimensional topology reveals phenomena like exotic spheres, manifolds that are topologically equivalent to spheres but geometrically different. In four dimensions, there are uncountably many distinct smooth structures on topological spheres. Lie groups represent continuous symmetry groups that often arise as symmetries of higher dimensional spaces. These groups have rich mathematical structure and appear throughout physics as the symmetries underlying fundamental forces. The classification of simple Lie groups reveals deep connections between algebra and geometry. Homology and cohomology provide algebraic tools for studying topological properties of higher dimensional spaces. These techniques assign algebraic objects like groups or rings to geometric spaces, enabling the study of topological properties through algebraic methods. The different dimensions support different types of topological phenomena. The mathematics of embedding describes how lower dimensional spaces can be placed within higher dimensional spaces. Whitney's embedding theorem shows that any undimensional manifold can be embedded in two n-dimensional Euclidean space, providing upper bounds on the dimensional requirements for containing complex geometric structures. Algebraic topology reveals how geometric properties connect to algebraic structures in ways that become increasingly rich in higher dimensions. Fundamental groups, homology groups, and homotopy groups provide different perspectives on the topological structure of spaces, with higher dimensions supporting more complex topological phenomena. Clifford algebras generalize complex numbers and quaternions to arbitrary dimensions, providing mathematical frameworks for describing rotations and reflections in higher dimensional spaces. These algebraic structures appear in physics as the mathematics underlying spinors and fermionic particles. The mathematics of optimization in higher dimensions encounters the curse of dimensionality. Many algorithms become exponentially more difficult as the number of dimensions increases. This mathematical challenge affects both practical computations and theoretical understanding of higher dimensional spaces. Probability theory in higher dimensions reveals counterintuitive phenomena like the concentration of measure, where random points in high-dimensional spaces tend to be nearly equidistant from each other and from the center. These effects arise because volume concentrates near the boundary of high-dimensional spheres. Fourier analysis extends to arbitrary dimensions through multivariate Fourier transforms that decompose functions into frequency components along each dimensional direction. Higher dimensional Fourier analysis provides tools for studying wave propagation, quantum mechanics, and signal processing in complex spaces. The mathematical study of higher dimensional spaces reveals deep connections between geometry, algebra, and analysis that weren't apparent when these fields developed independently. Modern mathematics increasingly relies on higher dimensional thinking to understand fundamental structures and relationships. Computational approaches to higher dimensional mathematics involve specialized algorithms and visualization techniques. While direct visualization becomes impossible beyond 3 dimensions, mathematical software can compute properties, generate projections, and explore relationships in spaces of arbitrary dimension. The unreasonable effectiveness of higher dimensional mathematics in physics suggests deep connections between mathematical abstraction and physical reality. Many mathematical structures developed for purely theoretical reasons later found applications in physics, suggesting that mathematics provides a window into the fundamental structure of reality. Perhaps most remarkably, higher dimensional mathematics reveals that our 3-dimensional geometric intuition represents just a tiny fraction of the mathematical possibilities for spatial structure. The rich mathematical world beyond 3 dimensions provides the theoretical foundation for understanding modern physics theories that propose reality itself transcends our everyday dimensional experience. As we'll explore next, these mathematical insights become crucial for understanding string theory and other modern physics frameworks that suggest our universe actually contains many more dimensions than the 3 we directly experience. Chapter 4. String Theory and Extra Dimensions. String theory represents humanity's most ambitious attempt to understand the fundamental nature of reality, proposing that everything in the universe, from electrons and quarks to space and time itself, emerges from tiny vibrating strings moving through a space containing not just our familiar 3 dimensions, but at least 6 additional spatial dimensions curled up at every point in space. This radical reimagining of dimensional reality offers potential explanations for why we observe exactly 3 large dimensions. The mathematical consistency of string theory requires specific numbers of spatial dimensions to work properly. The earliest version, Bosnick string theory, demands 26 spatial dimensions for mathematical consistency. Superstring theory, which includes fermionic particles and is more physically realistic, requires exactly 10 dimensions to 9 spatial dimensions plus time. These dimensional requirements aren't arbitrary choices, but emerge from the mathematical structure of the theory itself. Dr. Michael Green and John Schwartz demonstrated in 1984 that superstring theory avoids certain mathematical inconsistencies called anomalies only exactly 10 dimensions. This first superstring revolution showed that string theory provides a mathematically consistent framework for quantum gravity, but only if space contains 6 more dimensions beyond the 3 we observe. The extra dimensions in string theory are typically assumed to be compactified, curled up into geometric shapes so small that we cannot detect them directly. These compact dimensions exist at every point in our familiar 3-dimensional space, but with characteristic sizes around the Planck length of 10 to 35 meters, far smaller than anything we can measure with current technology. Calabi-Yau manifolds represent the most studied candidates for the geometry of these compact extra dimensions. These complex mathematical objects are 6-dimensional spaces with special geometric properties that preserve certain symmetries required by string theory. The specific shape of the Calabi-Yau manifold determines what kinds of particles and forces emerge in the 3-dimensional world we experience. Different Calabi-Yau manifolds lead to different low-energy physics, different particles, different force strengths, and different physical constants. The number of possible Calabi-Yau manifolds is enormous, potentially exceeding 10,500 different geometries. This landscape of string theory vacua suggests that many different versions of physics might be possible depending on how extra dimensions are compactified. The mechanism that determines which dimensions remain large while others compactify represents one of the deepest unsolved problems in string theory. Some process during the early universe must have selected 3 dimensions to remain macroscopic while the other 6 dimensions shrank to microscopic sizes. Understanding this selection process might explain why our universe has exactly 3 large spatial dimensions. Flux compactification represents one approach to understanding dimensional selection, involving background fields that thread through the extra dimensions and provide energy that determines their size. Different flux configurations can stabilize extra dimensions at different sizes, potentially explaining why some dimensions remain large while others stay small. Dr. Shamit Kakru and his colleagues have developed models where extra dimensions are stabilized by complex interplays between quantum effects, classical forces, and topological properties of the compact manifolds. These models suggest that dimensional selection might emerge naturally from string theory dynamics rather than requiring special initial conditions. The warped extra dimension scenarios pioneered by Dr. Lisa Randall and Raymond Sundram propose that extra dimensions might be large but hidden from us by warped geometry that confines ordinary matter and forces to 3-dimensional surfaces called branes embedded in higher dimensional space. In these models, we live on a 3-dimensional brane floating in higher dimensional space. Brand new models suggest that gravity can propagate through all dimensions while other forces are confined to our 3-dimensional brane. This could explain why gravity appears much weaker than other forces. Its strength gets diluted by spreading through extra dimensions, while electromagnetic and nuclear forces remain concentrated in 3 dimensions. Large extra dimensions represent another theoretical possibility, where extra dimensions could be as large as millimeters, but still remain undetected because only gravity propagates through them. Dr. Nima Arkani-Hamd, Savas Dimopoulos, and Jihad Valley showed that such large extra dimensions could solve the hierarchy problem, explaining why gravity is so much weaker than other forces. Experimental searches for extra dimensions include tests of Newton's inverse square, law for gravity at short distances, searches for missing energy in particle collisions that could escape into extra dimensions, and precision measurements of fundamental constants that might vary if extra dimensions exist. The Large Hadron Collider has searched for signatures of extra dimensions through particle production processes that would create microscopic black holes or other exotic objects if extra dimensions exist at accessible energy scales. While no definitive evidence has been found, these experiments continue to constrain theoretical models. Kaluza-Klein theory, developed in the 1920s, provided an early example of how extra dimensions could unify different forces. By adding a 5th dimension to Einstein's 4-dimensional spacetime, Theodore Kaluza and Oscar Klein showed how electromagnetism and gravity could be unified as different aspects of geometry in 5-dimensional space. The mathematical structure of Kaluza-Klein theory demonstrates how particles moving in compact, extra dimensions appear as different particle types when viewed from the perspective of lower dimensional observers. A single particle moving in a circular extra dimension appears as an infinite tower of particles with different masses in 4 dimensions. Dimensional transmutation represents a mechanism where physics at different energy scales corresponds to different effective numbers of dimensions. At very high energies, all dimensions might be accessible. At lower energies, extra dimensions become effectively frozen out, leaving only 3 dimensions dynamically active. The connection between extra dimensions and fundamental constants suggests that the sizes and shapes of compact dimensions determine the values of physical constants we measure. If extra dimensions evolved or changed size over cosmic time, fundamental constants might vary in ways that could be detectable through astronomical observations. M-theory extends string theory to include 11-dimensional supergravity as a fundamental framework. In the theory, what appear as different string theories in 10 dimensions are actually different perspectives on a single 11-dimensional theory. The 11th dimension might be extended rather than compact, leading to even richer geometric possibilities. ADS-CFT correspondence, discovered by Dr. Juan Maldacena, relates string theory in higher dimensional anti-de Sitter space to conformal field theories in lower dimensional space. This holographic principle suggests that physics in higher dimensions might be equivalent to physics in lower dimensions, potentially explaining how three-dimensional physics emerges from higher dimensional reality. The holographic principle has profound implications for understanding dimensionality, suggesting that the information content of any region of space is determined by the area of its boundary rather than its volume. This principle might explain why we experience three-dimensional physics, even if reality is fundamentally higher dimensional. Supersymmetry breaking in string theory compactifications affects how extra dimensions stabilize and what low-energy physics emerges. Different mechanisms for supersymmetry breaking lead to different predictions for particle masses, force strengths, and cosmological evolution, potentially explaining fine-tuning problems in the standard model. The anthropic principle in string theory suggests that among the enormous number of possible compactifications, only a tiny fraction leads to universes capable of supporting complex chemistry and life. We might observe three large dimensions simply because most other dimensional configurations don't support observers. Dynamic dimensional selection represents theoretical scenarios where the number of large dimensions could change over cosmic time through phase transitions or evolutionary processes. Early in cosmic history, more dimensions might have been large, with the current three-dimensional configuration emerging through cosmic evolution. Perhaps most remarkably, string theory suggests that asking, "Why does space have three dimensions?" might be the wrong question. Instead, space might fundamentally be higher dimensional, with three-dimensional physics emerging as a low-energy approximation to more complex higher dimensional dynamics. Understanding why we observe three dimensions requires understanding how higher dimensional physics reduces to lower dimensional effective theories. The mathematical richness of string theory in higher dimensions provides a theoretical framework for understanding how dimensional structure connects to particle physics, cosmology, and quantum gravity. Whether string theory describes reality remains an open question, but its mathematical insights into extra dimensions have revolutionized how physicists think about the nature of space itself. As we'll explore next, the stability requirements for complex structures in different dimensions provide another perspective on why three-dimensional space might be uniquely suited for the emergence of complexity and life. Chapter 5: Stability and Complexity. The emergence of complex structures, from atoms and molecules to planets and living organisms, depends critically on achieving delicate balances between competing forces. And these balance points exist only within narrow ranges that are uniquely satisfied in three-dimensional space. Understanding how stability requirements change with dimensionality reveals why three dimensions provide the optimal framework for complexity to emerge and persist over cosmic timescales. Atomic stability represents the most fundamental requirement for any complex chemistry. In our three-dimensional universe, atoms achieve stability through quantum mechanical energy levels that emerge from solving Schrodinger's equation in three-dimensional space. The familiar electron shells, SPD, and F orbitals have specific three-dimensional shapes that enable chemical bonding and create the periodic table S-rich structure. Dr. Freeman Dyson's analysis of atomic stability in different dimensions shows that stable atoms require exactly three spatial dimensions. In two-dimensional space, the attractive Coulomb potential between electrons and nuclei becomes too strong, causing electron wave functions to collapse into the nucleus. In four or more dimensions, the potential weakens so rapidly with distance that bound states become extremely fragile. The mathematics underlying atomic stability involves balancing kinetic energy from quantum mechanical motion against potential energy from electromagnetic attraction. This balance depends critically on how potentials scale with distance, which changes with spatial dimensionality. Only 3 dimensions provide the specific scaling relationships that enable stable atomic structure over the energy ranges relevant for chemistry. Molecular bonding depends on electron wave functions overlapping between adjacent atoms, creating shared electron distributions that bind atoms into molecules. The 3-dimensional shapes of electron orbitals determine which atoms can bond together and at what angles, enabling the geometric complexity that makes organic chemistry possible. In different dimensional spaces, electron orbitals would have completely different shapes and symmetries, fundamentally altering chemical bonding patterns. 2-dimensional molecules would be confined to flat sheets with limited structural complexity. 4-dimensional molecules could adopt geometric configurations impossible to achieve in 3 dimensions, but might be too unstable to persist. The scaling relationships between surface area and volume become crucial for understanding stability in different dimensions. 3-dimensional objects have surface area that scales as length squared, while volume scales as length cubed. This square-cube law affects everything from material strength to heat transfer to biological metabolism. Engineering structures rely on 3-dimensional scaling relationships to achieve strength and stability. The weight of a structure scales with its volume, length cubed, while the strength of its supporting members scales with their cross-sectional area, length squared. This creates fundamental size limits for 3-dimensional structures that would be completely different in other dimensional spaces. Biological systems exploit 3-dimensional scaling relationships in countless ways. Blood circulation depends on vessels with cross-sectional areas that scale appropriately to supply organs, whose thus volumes scale with different power laws. Skeletal systems provide support for masses that scale with bone lengths in ways that work only in 3 dimensions. Dr. J. B. S. Haldane explored biological scaling relationships in his famous essay on Being the Right Size, showing how fundamental physical constraints determine optimal sizes for different types of organisms. These scaling laws emerge from 3-dimensional geometry and would be completely different in spaces with other numbers of dimensions. Planetary formation and orbital stability require 3-dimensional gravitational dynamics to enable stable configurations that persist over billions of years. The inverse square law for gravity in 3 dimensions allows for stable closed orbits with specific mathematical properties that enable planetary systems to form and evolve. In 2-dimensional space, gravitational orbits are fundamentally unstable due to the mathematical properties of the inverse first power force law. Small perturbations cause orbits to either decay rapidly or escape to infinity, preventing the formation of stable planetary systems that could support long-term chemical and biological evolution. 4-dimensional gravity follows an inverse cube law that makes gravitational binding extremely weak at large distances. Planetary orbits would be so fragile that even tiny perturbations would disrupt them. The formation of stable stellar systems would be nearly impossible, preventing the long-term stability needed for biological evolution. Stellar structure depends on achieving hydrostatic equilibrium between gravitational attraction and radiation pressure from nuclear fusion. This balance involves 3-dimensional relationships between mass distribution, energy generation, and energy transport that determine stellar lifetimes and evolutionary pathways. The nuclear fusion processes that power stars depend on quantum tunneling probabilities that change with spatial dimensionality. The specific energy levels and reaction cross-sections for nuclear reactions evolved within 3-dimensional physics. Different dimensional spaces might not support the nuclear chemistry needed for stellar energy generation. Fluid dynamics and turbulence behave differently in different numbers of dimensions, affecting everything from weather systems to blood circulation to stellar convection. 3-dimensional turbulence has specific mathematical properties that enable energy cascades and mixing processes that might not occur in other dimensional spaces. The formation of complex structures requires mechanisms for organizing matter into patterns that persist over time. Three-dimensional space provides unique opportunities for mechanical linkages, chemical networks, and information storage systems that depend on specific geometric relationships between components. Information processing systems, from digital computers to biological brains, rely on three-dimensional architectures that enable complex connectivity patterns while maintaining physical realizability. Neural networks achieve their computational power through three-dimensional connection patterns that would be impossible in lower dimensions and might be too complex to implement stably in higher dimensions. Self-organization processes that create complex structures from simple components depend on local interactions that scale appropriately with system size. Three-dimensional space provides specific scaling relationships between local and global effects that enable emergent complexity to develop and persist. Phase transitions and critical phenomena occur differently in different numbers of dimensions, potentially affecting how complex structures can form through spontaneous symmetry breaking and other self-organization mechanisms. Three-dimensional space supports specific types of phase transitions that might be essential for complexity. The mathematical theory of dynamical systems reveals how stability depends on the number of dimensions available for system evolution. Three-dimensional phase spaces provide sufficient richness for complex dynamics while remaining sufficiently constrained that stable attractors can exist and persist over long time periods. Network theory shows how complex connectivity patterns depend on the dimensionality of the embedding space. Three-dimensional networks can achieve optimal balances between local connectivity and global integration that enable both specialization and coordination in complex systems. Error correction and fault tolerance in complex systems benefit from three-dimensional redundancy patterns that provide robustness against component failures while minimizing resource requirements. These error correction schemes depend on geometric properties specific to three-dimensional space. The mathematical frameworks for understanding complexity, including chaos theory, network science, and information theory, reveal deep connections between dimensional structure and emergent complexity. Three dimensions appear to provide a unique balance that enables complexity to emerge while remaining stable enough to persist and evolve. Perhaps most remarkably, the stability requirements for complex structures suggest that three-dimensional space occupies a unique position in the landscape of possible dimensional configurations. Lower dimensions lack sufficient richness for complexity, while higher dimensions may provide too many degrees of freedom for stable structures to persist over the timescales needed for evolution and development. The relationship between stability and complexity in three-dimensional space might explain not only why our universe has three large spatial dimensions, but also why these dimensions enable the case emergence of observers capable of asking questions about dimensional structure in the first place. Understanding stability requirements provides a physical principle that could complement or replace anthropic arguments for three-dimensional space. As we'll explore next, the anthropic principle provides another perspective on dimensional selection, suggesting that we observe three spatial dimensions because other dimensional configurations cannot support the complex structures necessary for conscious observers. Chapter 6. The Anthropic Principle. The anthropic principle offers a radically different perspective on why space has three dimensions. Perhaps we observe exactly three spatial dimensions, not because of fundamental physical laws, but because universes with other numbers of dimensions cannot support the complex chemistry, stable structures, and information processing systems necessary for conscious observers to exist and ask questions about dimensional structure. The weak anthropic principle, formulated by Dr. Brandon Carter in 1974, states that observed physical parameters must be compatible with the existence of observers who can make observations. Applied to dimensional structure, This principle suggests that if most possible universes have numbers of dimensions incompatible with complexity and life, then conscious beings would inevitably find themselves in universes like ours, with exactly 3 large spatial dimensions. The strong anthropic principle goes further, proposing that the universe must have properties that allow conscious observers to develop at some point in its evolution. This stronger version suggests that dimensional structure, fundamental constants, and physical laws are somehow constrained or selected to ensure that complexity and consciousness can emerge. Dr. Steven Winberg has argued that anthropic reasoning becomes scientifically meaningful when applied to theories that predict large numbers of possible universes with different properties, such as the string theory landscape with its enormous number of possible compactifications. If most string theory vacua lead to universes incompatible with observers, anthropic selection could explain our observed dimensional structure. The multiverse hypothesis provides a framework where anthropic reasoning becomes testable. If cosmic inflation or other mechanisms create enormous numbers of causally disconnected regions with different physical properties, then anthropic selection could determine which types of regions contain observers capable of measuring dimensional structure. 2-dimensional universes face fundamental obstacles to supporting complex chemistry and life. The constraint of motion to a plane prevents the formation of complex 3-dimensional molecular structures essential for biochemistry. Additionally, circulatory systems, nervous systems, and other biological networks would face topological limitations in 2-dimensional space that might prevent complex organisms from developing. Dr. Edwin Abbott's Flatland explored some challenges that 2-dimensional beings would face, including difficulties with digestion, food passages would divide the body, and circulation, blood vessels couldn't cross without intersecting. While fictional, these examples illustrate real topological constraints that would limit biological complexity in 2-dimensional space. 4-dimensional space would present different challenges for biological systems. While offering more geometric possibilities for complex structures, 4-dimensional space would dramatically alter fundamental physics in ways that might prevent stable chemistry from developing. The rapid fall-off of gravitational and electromagnetic forces could make atomic binding unstable and planetary systems impossible. The mathematical analysis of biological functions in different dimensions reveals specific requirements for complexity that appear to be uniquely satisfied in 3-dimensional space. Circulatory systems need to deliver nutrients throughout 3-dimensional volumes while maintaining pressure gradients. Nervous systems require complex 3-dimensional connectivity patterns for information processing. Brain function depends critically on 3-dimensional neural network architectures that enable both local processing and long-range communication. 2-dimensional neural networks would have severely limited connectivity options, while 4-dimensional networks might be too complex to develop and maintain efficiently. The anthropic bound on dimensional structure can be made quantitative by calculating the probability that randomly selected dimensional configurations could support observers. If we assume that observer-compatible universes are extremely rare in the space of all possible dimensional structures, then finding ourselves in a 3-dimensional universe becomes statistically expected rather than surprising. Cosmological evolution in different dimensions would follow different pathways that affect the possibility of developing complex structures over cosmic timescales. 3-dimensional space allows for stellar formation, planetary system stability, and chemical evolution that provide the necessary conditions for biological development. The fine-tuning problem in cosmology extends to dimensional structure. Not only must fundamental constants lie within narrow ranges for life, but the number of spatial dimensions must also fall within the narrow range that enables complex chemistry. Adding dimensional fine-tuning to other cosmological fine-tuning arguments strengthens the case for anthropic explanations. Dr. Max Tegmark has analyzed the anthropic constraints on fundamental constants and dimensional structure. showing that small changes in either could prevent the formation of stars, planets, atoms, or other structures necessary for life. The combination of multiple fine-tuning requirements makes accidental occurrence increasingly implausible. The doomsday argument represents one criticism of anthropic reasoning, suggesting that anthropic logic leads to problematic conclusions about the future survival of humanity and consciousness. However, these criticisms may not apply to dimensional structure, which appears to be a fixed property of physical law rather than an evolving parameter. Observer selection effects complicate anthropic arguments by raising questions about which types of observers should be considered in anthropic calculations. Different assumptions about observer properties lead to different anthropic predictions, potentially weakening the explanatory power of anthropic reasoning. The reference class problem asks which observers should be included in anthropic calculations. Should we consider all possible conscious beings, only human-like intelligence, or some other category? Different choices lead to different anthropic predictions about dimensional structure and other physical parameters. Quantum cosmology and the many worlds interpretation of quantum mechanics provide alternative frameworks for anthropic reasoning. If quantum mechanics creates branching universes with different properties, anthropic selection could operate through quantum measurement processes rather than requiring multiple classical universes. The principle of mediocrity suggests that we should expect to find ourselves in typical rather than exceptional circumstances. Applied to dimensional structure, this principle might predict that three-dimensional space is the most common dimensional configuration in multiverse scenarios, rather than requiring special anthropic selection. Information-theoretic approaches to anthropic reasoning focus on the complexity and information processing requirements for observers rather than biological details. These approaches might provide more fundamental constraints on dimensional structure by identifying mathematical requirements for information storage and computation. The simulation hypothesis raises questions about anthropic reasoning by suggesting that observed reality might be computed rather than physical. If consciousness can exist in simulated environments, anthropic constraints on physical dimensional structure might be less restrictive than biological arguments suggest. Evolutionary approaches to cosmology propose that universes evolve through mechanisms analogous to biological evolution, with selection pressures favoring dimensional configurations that enable complexity and possibly consciousness. These scenarios could provide alternatives to anthropic reasoning while reaching similar conclusions about dimensional selection. The participatory anthropic principle, developed by Dr. John Wheeler, suggests that consciousness plays a fundamental role in determining physical reality through quantum measurement processes. This approach might provide deeper explanations for dimensional structure by connecting observation to the fundamental nature of space and time. Testability remains a significant challenge for anthropic explanations of dimensional structure. While anthropic reasoning can explain why we observe three dimensions, it's difficult to design experiments that could falsify anthropic hypotheses or distinguish them from alternative explanations based on fundamental physics. The landscape of string theory provides a concrete framework where anthropic reasoning could be tested by comparing anthropic predictions with detailed calculations of how different compactifications affect low-energy physics. If anthropic selection successfully predicts which types of compactifications are observed, this would support anthropic explanations. Perhaps most importantly, anthropic reasoning about dimensional structure reveals deep connections between the existence of consciousness and the fundamental properties of space itself. Whether or not anthropic explanations ultimately prove correct, they highlight the remarkable fact that dimensional structure appears precisely tuned to enable the emergence of observers capable of contemplating their own existence. The anthropic perspective on dimensional structure also raises profound philosophical questions about the relationship between mind and reality, the nature of existence, and the possibility that consciousness plays a fundamental role in determining the structure of physical law rather than merely being an emergent consequence of complex physical processes. As we'll explore next, cosmological models provide another approach to understanding dimensional selection, suggesting that the number of large spatial dimensions might have been determined during the universe's earliest moments through dynamical processes rather than anthropic selection. Chapter 7. Cosmological Dimensional Selection. The earliest moments of cosmic history might hold the key to understanding why space has 3 dimensions with cosmological models, suggesting that dimensional structure was determined dynamically during the universe's first fraction of a second, through phase transitions, symmetry breaking, and other physical processes that selected 3 dimensions to remain large while others compactified or never developed. Cosmic inflation provides a natural framework for understanding dimensional selection through its ability to stretch quantum fluctuations to macroscopic scales while potentially suppressing or amplifying different dimensional directions differently. During the inflationary epoch, space expanded exponentially while undergoing quantum field fluctuations that might have determined which dimensions would remain accessible. The pre-inflationary universe might have possessed different dimensional structure than what we observe today. Some cosmological models propose that space initially contained different numbers of large dimensions, with inflation selectively stretching 3 directions while leaving others compact or causing them to contract back to subatomic scales. Dr. Alan Gouth's original inflation model involved scalar fields rolling down potential energy curves, and these dynamics could potentially distinguish between different spatial directions. If the inflationary mechanism couples differently to different dimensional directions, it might naturally select 3 dimensions for exponential expansion. Spontaneous symmetry breaking during cosmic phase transitions provides another mechanism for dimensional selection. Just as spontaneous symmetry breaking can determine the masses of particles and the relative strengths of fundamental forces, it might also determine which spatial dimensions remain large and which become compact. The mathematical framework of symmetry breaking in higher dimensional spaces involves scalar fields that acquire vacuum expectation values pointing in specific directions in field space. These directions could correspond to specific dimensional configurations, with symmetry breaking selecting which dimensions remain accessible at low energies. Kaluza-Klein cosmology explores how extra dimensions evolve during cosmic expansion, with different dimensions potentially having different scale factors that evolve according to the Einstein field equations in higher dimensional spacetime. Some dimensions might grow during cosmic expansion, while others shrink or remain static. Dr. Edward Kolb and his colleagues have developed models where extra dimensions undergo accelerated contraction, while our familiar 3 dimensions undergo accelerated expansion. These scenarios naturally explain why we observe exactly 3 large spatial dimensions, without requiring special initial conditions. Phase transitions in the early universe could trigger dimensional compactification through mechanisms similar to those that generate particle masses and determine force strengths. The electroweak phase transition, grand unification phase transitions, and potentially even earlier transitions might influence dimensional structure. String cosmology provides specific models for dimensional evolution during the universe's earliest moments. In these scenarios, the Dilaton field that controls string coupling could also influence the sizes of extra dimensions, potentially causing some to grow while others shrink during cosmic evolution. The landscape of string theory vacua includes solutions where different numbers of dimensions are large, suggesting that dimensional selection might occur through cosmological evolution between different vacuum states. Transitions between these states could change the effective dimensionality of space over cosmic time. Flux compactification in string theory involves background fields threading extra dimensions and providing energy that determines their sizes. Different flux configurations could be selected during cosmic evolution, potentially explaining why specific dimensional configurations are realized in our universe. Anthropic inflation scenarios combine cosmic inflation with anthropic reasoning, proposing that inflation creates enormous numbers of causally disconnected regions with different dimensional configurations. Observer selection then explains why we find ourselves in regions with 3 large spatial dimensions. The eternal inflation framework suggests that different regions of space could undergo inflation with different dimensional outcomes. While most regions might end up with dimensional configurations incompatible with complexity, a small fraction could produce observer-compatible 3-dimensional regions. Cyclic cosmology models propose that the universe undergoes repeated cycles of expansion and contraction, potentially allowing dimensional structure to evolve over multiple cosmic cycles. The number of large dimensions could change between cycles, with 3-dimensional configurations being selected through cosmic evolution. Ekpyrotic and brane collision scenarios involve higher dimensional branes colliding to create 4-dimensional spacetime, potentially explaining why exactly 3 spatial dimensions plus time emerge from higher dimensional physics. The dynamics of brane collisions could naturally select specific dimensional outcomes. The role of dark energy in dimensional selection remains an active area of research. Some models propose that dark energy is related to the energy stored in compact extra dimensions, with the acceleration of cosmic expansion reflecting the evolution of higher dimensional structure. Quantum cosmology approaches dimensional selection through the Wheeler-DeWitt equation and other frameworks for quantum gravity. These approaches might predict which dimensional configurations are most likely to emerge from quantum creation, events, or quantum transitions between different vacuum states. The Hartle-Hawking no-boundary proposal suggests that spacetime emerges from purely quantum mechanical processes without classical initial conditions. In this framework, dimensional structure could be determined by quantum probability amplitudes that favor specific dimensional configurations. Causal set theory and other approaches to quantum gravity propose that spacetime emerges from more fundamental discrete structures. These approaches might provide natural mechanisms for dimensional selection by determining which types of dimensional structures can emerge from fundamental quantum processes. Loop quantum cosmology explores how quantum effects near the Planck scale affect cosmic evolution and potentially determine dimensional structure. Quantum-bound scenarios might select specific dimensional configurations through quantum mechanical processes operating during the universe's earliest moments. The cosmic microwave background radiation could potentially contain signatures of dimensional selection processes if they occurred during or after the epoch of last scattering. Future precision observations might detect subtle features that constrain models of dimensional evolution. Primordial gravitational waves could carry information about dimensional structure during the earliest cosmic epochs, potentially providing observational tests of models that predict dimensional selection during inflation or other early universe processes. The formation of cosmic structure could be influenced by dimensional selection processes if they affected the spectrum of primordial density fluctuations or the evolution of perturbations during cosmic expansion. Galaxy formation and large-scale structure might encode information about dimensional evolution. Dark matter and dark energy might be connected to dimensional selection processes if these components arise from physics involving extra dimensions. Understanding dark sector interactions could provide clues about why specific dimensional configurations are realized. Precision tests of general relativity could reveal signatures of dimensional selection if the process left residual effects that modify gravitational dynamics at specific scales. Space-based gravitational wave detectors might be sensitive to such effects. The unification of quantum mechanics and general relativity might be impossible without understanding dimensional selection, as any complete theory of quantum gravity must explain why spacetime has the dimensional structure we observe rather than any of the other mathematically consistent possibilities. Future cosmological observations with next-generation telescopes could potentially detect signatures of dimensional selection processes through their effects on cosmic evolution, structure formation, or the thermal history of the universe. Perhaps most remarkably, cosmological dimensional selection suggests that the apparently static three-dimensional structure of space might actually be the result of dynamical evolution during the universe's earliest moments. Understanding this evolution could provide insights into the nature of space, time, and the fundamental laws that govern cosmic development. The study of cosmological dimensional selection also reveals deep connections between the largest scales of cosmic evolution and the smallest scales of fundamental physics, suggesting that understanding why space has three dimensions requires understanding both quantum gravity and cosmic evolution. As we'll explore next, experimental efforts to detect extra dimensions provide ways to test whether space actually contains more dimensions than we directly experience, potentially revealing whether dimensional selection processes have hidden rather than eliminated higher dimensional structure. Chapter 8. Experimental Searches. The search for evidence of extra spatial dimensions represents one of the most challenging experimental programs in modern physics, requiring ingenious techniques to detect dimensional effects that might be hidden at scales far smaller than current technology can directly probe, or geometrically confined in ways that make them nearly impossible to access through ordinary matter and forces. Gravitational tests provide the most direct approach to searching for extra dimensions because gravity is the only known force that might propagate through additional spatial dimensions rather than being confined to the three dimensions we experience. If extra dimensions exist, gravity could leak into them, causing deviations from Newton's inverse square law at distances where extra-dimensional effects become important. The inverse square law for gravity has been tested with extraordinary precision at distances ranging from cosmic scales down to fractions of millimeters. These tests search for deviations that would indicate gravitational flux spreading into extra dimensions, which would cause gravitational attraction to fall off faster than the familiar 1r² relationship at short distances. Dr. Eric Adelberger and his colleagues at the University of Washington have conducted the most precise short-range gravity experiments, using torsion balances to measure gravitational forces between test masses separated by distances as small as 0.05 millimeters. These experiments constrain extra dimensions larger than about 0.1 millimeters, ruling out some large extra dimension scenarios. The Etwash Group's experiments involve exquisitely sensitive measurements of gravitational torques on specially designed test bodies with complex mass distributions. By measuring how gravitational interactions depend on distance and geometry, these experiments can detect extra-dimensional effects that would modify the familiar inverse square force law. Particle accelerator experiments search for extra-dimensional signatures through missing energy events, where some of the energy from high-energy collisions appears to escape into extra dimensions, carrying away momentum and energy that cannot be detected by particle detectors confined to three-dimensional space. The Large Hadron Collider has searched for extra-dimensional effects through several channels, including the production of microscopic black holes that would be possible if extra dimensions lower the scale of quantum gravity, and missing energy signatures from particles or radiation escaping into extra dimensions during high-energy collisions. Kaluza-Klein excitations represent another signature that accelerator experiments seek. If extra dimensions exist, particles moving in those dimensions would appear as towers of increasingly massive particles when viewed from three-dimensional perspective. Detecting these Kaluza-Klein modes would provide direct evidence for extra-dimensional structure. Dr. Savas Dimopoulos and his colleagues have calculated that large extra dimensions could lower the quantum gravity scale from the Planck scale of 1019 GeV down to energies accessible at particle accelerators. This would enable the production of microscopic black holes and other quantum gravitational effects in laboratory experiments. Precision measurements of fundamental constants provide indirect searches for extra dimensions by testing whether constants remain truly constant over time and space. If extra dimensions change size or configuration, they could affect the values of fundamental constants in ways detectable through astronomical observations and precision laboratory measurements. The fine structure constant, gravitational constant, and other fundamental parameters have been measured with increasing precision using atomic clocks, laser interferometry, and astronomical spectroscopy. Variations in these constants could indicate extra-dimensional evolution or spatial variation in dimensional structure. Astrophysical tests search for extra-dimensional effects in cosmic phenomena where gravitational energies reach scales comparable to fundamental physics. Neutron star mergers, black hole formation, and other extreme gravitational environments might reveal extra-dimensional physics through gravitational wave signatures or exotic energy loss mechanisms. Gravitational wave detectors like LIGO and Virgo provide new tools for probing dimensional structure by measuring how gravitational waves propagate through space. Extra dimensions could modify gravitational wave polarizations, propagation speeds, or energy loss rates in ways detectable by increasingly sensitive gravitational wave observatories. Dark matter searches might reveal extra-dimensional physics if dark matter consists of particles that can access extra dimensions, or if dark matter interactions are mediated by extra-dimensional physics. Underground detectors and space-based observatories search for dark matter signatures that could reveal higher dimensional structure. The hierarchy problem in particle physics, why gravity is so much weaker than other forces, could be resolved by extra-dimensional physics. If gravity spreads through extra dimensions while other forces remain confined to 3 dimensions, this would naturally explain the observed weakness of gravitational interactions. Supersymmetry searches at particle accelerators could reveal extra-dimensional physics if supersymmetric particles preferentially interact through extra-dimensional channels. The absence of observed supersymmetric particles at current energy scales constrains but doesn't rule out extra-dimensional scenarios. Cosmological observations provide large-scale tests of dimensional structure through their sensitivity to how gravity operates on cosmic scales. Precision measurements of cosmic expansion, structure formation, and primordial nucleosynthesis constrain extra-dimensional models that would modify cosmic evolution. The cosmic microwave background radiation encodes information about cosmic geometry and gravitational dynamics during the epoch of last scattering. Extra-dimensional effects could modify the predicted patterns of temperature fluctuations in ways detectable by precision cosmological observatories. Tabletop experiments testing equivalence principles search for violations that could indicate extra-dimensional interactions affecting different types of matter differently. These experiments can achieve extraordinary precision by measuring whether different materials fall at exactly the same rate in gravitational fields. Atomic interferometry experiments use quantum mechanical techniques to measure gravitational effects with unprecedented sensitivity. These experiments could potentially detect extra-dimensional modifications to gravitational interactions that are too small to detect through classical gravitational measurements. Quantum mechanics experiments explore whether quantum effects reveal extra-dimensional structure through modifications to energy levels, transition probabilities, or correlation functions that would differ from 3-dimensional predictions. High-precision spectroscopy of atomic energy levels provides tests of quantum electrodynamics and other fundamental theories that might be modified by extra-dimensional physics. Deviations from theoretical predictions could indicate extra-dimensional corrections to electromagnetic interactions. Neutrino oscillation experiments might reveal extra-dimensional physics if sterile neutrinos can access extra dimensions or if neutrino interactions are modified by higher dimensional structure. The observed pattern of neutrino masses and mixing angles could constrain extra-dimensional scenarios. Future experimental programs will push sensitivity to extra dimensions through improved gravitational tests, higher energy particle accelerators, more sensitive gravitational wave detectors, and novel quantum measurement techniques that could reveal subtle extra-dimensional effects. Space-based gravitational experiments could test Newton's inverse square law over much larger distance ranges than possible on Earth, potentially revealing extra-dimensional effects that operate at intermediate scales between laboratory and cosmic distances. Precision clock networks could detect spatial or temporal variations in fundamental constants that might result from extra-dimensional evolution or spatial variation in dimensional structure. These networks could provide three-dimensional maps of fundamental constant values. Next-generation particle accelerators might reach energy scales where extra-dimensional effects become directly observable through particle production, missing energy signatures, or modifications to well-established particle physics processes. Advanced quantum sensors and interferometers might achieve sensitivity to extra-dimensional effects through precision measurements of quantum mechanical phases, energy levels, or correlation functions that would be modified by higher dimensional physics. Perhaps most importantly, the experimental search for extra dimensions represents humanity's effort to test whether reality extends beyond our direct sensory experience into hidden dimensions of space. These experiments probe fundamental questions about the nature of space itself and whether the three-dimensional world we experience represents the full extent of spatial reality. The absence of definitive experimental evidence for extra dimensions after decades of searching has constrained theoretical models while raising deeper questions about how extra dimensions might be hidden and what energy scales or distance ranges might be required to reveal them. As we'll explore next, the technological implications of extra-dimensional physics could be revolutionary if such dimensions exist and can be accessed, potentially enabling new forms of energy generation, communication, and transportation that currently seem like science fiction. Chapter 9. Technological Implications. The discovery and potential manipulation of extra-spatial dimensions could revolutionize technology in ways that fundamentally alter human civilization, opening possibilities for energy generation, communication systems, and transportation methods that transcend the apparent limitations imposed by three-dimensional space. Understanding these implications reveals how dimensional physics connects to practical applications that could transform society. Energy generation through extra-dimensional physics could provide virtually unlimited power by accessing energy sources unavailable in three-dimensional space. If extra dimensions contain energy fields or enable more efficient conversion of matter to energy, dimensional engineering could solve humanity's long-term energy challenges through entirely new physical mechanisms. Higher dimensional energy storage might enable energy densities far exceeding anything possible with three-dimensional technologies. Just as moving from two-dimensional surfaces to three-dimensional volumes dramatically increases storage capacity, accessing higher dimensional spaces could provide energy storage capabilities that dwarf current battery and fuel technologies. Dr. Michio Kaku has speculated that civilizations capable of manipulating extra dimensions could tap into zero-point energy fluctuations in higher dimensional spaces, potentially accessing energy reservoirs that exist throughout apparently empty space. While highly speculative, such technologies could provide energy sources independent of matter consumption. Transportation through extra dimensions could enable travel that appears to violate three-dimensional limitations by taking shortcuts through higher dimensional space. If matter could somehow access extra dimensions, travelers might move between distant three-dimensional locations through paths that are much shorter in higher dimensional space. The concept of hyperspace travel in science fiction reflects this possibility, using extra dimensions to travel vast distances in apparently short times. While current physics provides no mechanism for moving ordinary matter through compact extra dimensions, future advances in fundamental physics could reveal pathways for dimensional transportation. Wormhole physics represents one theoretical framework where extra-dimensional structure could enable faster-than-light travel through space-time shortcuts that connect distant regions of three-dimensional space. These exotic structures would require manipulation of higher dimensional geometry in ways far beyond current technology. Communication systems could potentially exploit extra dimensions to enable instantaneous information transmission across vast three-dimensional distances. If signals could propagate through extra dimensions without the speed of light limitations that constrain three-dimensional communication, this could revolutionize interstellar and even intergalactic communication. Quantum entanglement effects might be enhanced or modified by extra-dimensional physics in ways that enable practical quantum communication systems with capabilities exceeding those possible in three-dimensional space alone. Understanding how quantum mechanics operates in higher dimensions could reveal new communication possibilities. Information storage in higher dimensions could provide computational capabilities that are impossible to achieve with three-dimensional technologies. Just as moving from two-dimensional to three-dimensional storage dramatically increases information density, higher dimensional storage could enable unprecedented computational power. Quantum computing in extra dimensions might access computational resources unavailable to three-dimensional quantum systems. If quantum states can be extended into extra dimensions, quantum computers might achieve computational capabilities that exceed fundamental limitations on three-dimensional quantum information processing. Dr. Seth Lloyd and other quantum information theorists have explored how the computational capacity of physical systems scales with their dimensional structure. Higher dimensional quantum systems could potentially perform calculations that are impossible for three-dimensional systems of comparable size and energy. Manufacturing and construction could be revolutionized by access to extra dimensions, enabling the creation of materials and structures with properties impossible to achieve through three-dimensional engineering. Materials could have internal structure extending into extra dimensions while maintaining three-dimensional interfaces. Metamaterials with extra-dimensional structure could exhibit properties like negative refractive indices, perfect lensing, or exotic mechanical behaviors that arise from their higher dimensional internal structure. These materials could enable cloaking devices, perfect imaging systems, or ultra-strong materials with unprecedented properties. Architectural possibilities would expand dramatically if construction could somehow utilize extra-dimensional space for structural support, storage, or functionality, while maintaining three-dimensional accessibility for human occupants. Buildings could be larger inside than outside if they extend into extra dimensions. Medical technologies could benefit from extra-dimensional physics if biological systems could be diagnosed or treated using higher dimensional techniques. Medical imaging might reveal biological structure invisible to three-dimensional scanning methods if biology has extra-dimensional components. Drug delivery systems could potentially use extra-dimensional pathways to transport medications directly to target organs or cells through routes unavailable in three-dimensional space. This could enable unprecedented precision in medical treatments while minimizing side effects. Surgical techniques might exploit extra-dimensional access to reach internal body structures without invasive three-dimensional procedures. Surgeons might manipulate internal organs through extra-dimensional pathways that don't require cutting through intervening tissues. Military applications of extra-dimensional technology could include weapon systems, defense mechanisms, and reconnaissance capabilities that operate through higher dimensional space. However, such applications raise profound ethical questions about the responsible development of dimensional technologies. Stealth technology could theoretically use extra dimensions to hide objects from three-dimensional detection methods by storing parts of their structure in inaccessible dimensional spaces. Surveillance systems might conversely use extra-dimensional physics to detect hidden objects or activities. Environmental applications could include waste disposal systems that transfer harmful materials into extra-dimensional spaces where they cannot affect three-dimensional ecosystems. However, such applications would require careful analysis of environmental consequences in higher dimensional contexts. Clean energy technologies might exploit extra-dimensional physics to achieve fusion reactions, antimatter generation, or other energy production methods with higher efficiency and fewer environmental consequences than current energy technologies. Economic implications of extra-dimensional technologies could be transformative, potentially obsoleting entire industries while creating entirely new economic sectors based on higher dimensional physics. The economic disruption could exceed that from any previous technological revolution. Intellectual property issues would become complex for technologies that operate partially through extra dimensions. Legal frameworks would need to address questions about ownership and regulation of higher dimensional technologies and their effects. Security concerns arise from the potential for extra-dimensional technologies to enable surveillance, weapon systems, or other applications that could threaten privacy, security, or stability. International cooperation would be essential for managing dimensional technologies responsibly. Research and development priorities would shift dramatically if extra dimensions became technologically accessible. Scientific funding and industrial research would likely focus heavily on understanding and exploiting higher dimensional physics for practical applications. Educational systems would need to prepare students for careers involving extra-dimensional technologies, requiring new mathematical and scientific curricula that extend far beyond current three-dimensional focus in science and engineering education. Ethical frameworks would need development to address questions about the responsible use of extra-dimensional technologies, particularly those with potential for environmental damage, social disruption, or military applications. The timeline for developing extra-dimensional technologies remains highly uncertain and depends on fundamental advances in theoretical physics, experimental techniques for accessing extra dimensions, and engineering capabilities for manipulating higher dimensional structure. Current limitations include the lack of any confirmed evidence for accessible extra dimensions, the absence of mechanisms for moving matter or energy through extra-dimensional spaces, and the enormous energy scales that might be required for dimensional manipulation. Future breakthroughs might come from advances in string theory, quantum gravity, high-energy physics experiments, or entirely unexpected discoveries about the nature of space itself. The development of extra-dimensional technologies could require scientific revolutions comparable to quantum mechanics or relativity. Perhaps most importantly, the potential technological implications of extra dimensions illustrate how fundamental questions about the nature of space could have practical consequences that transform human civilization. Whether or not extra-dimensional technologies ever become feasible, considering their possibilities reveals the profound connections between abstract physics and practical human needs. The responsible development of any extra-dimensional technologies would require unprecedented international cooperation, careful environmental and safety assessment, and ethical frameworks that consider the global implications of technologies that could transcend three-dimensional limitations. As we'll explore next, the philosophical implications of extra dimensions raise deep questions about the nature of reality, consciousness, and our place in a potentially much larger and stranger universe than our three-dimensional experience suggests. Chapter 10. Philosophical Implications. The possibility that space contains more than three dimensions challenges fundamental assumptions about reality, consciousness, and the nature of existence itself, raising profound philosophical questions about what we can know, what we can experience, and whether our three-dimensional perspective provides an accurate or severely limited view of the true structure of reality. The relationship between dimensional structure and consciousness represents one of the deepest philosophical puzzles raised by extra-dimensional physics. If reality is fundamentally higher dimensional, but consciousness is somehow confined to three-dimensional experience, this suggests that awareness itself might be dimensionally constrained in ways that limit our access to the full structure of existence. Dr. Edwin Abbott's Flatland provides a thought experiment about dimensional consciousness. By imagining how two-dimensional beings might perceive three-dimensional objects passing through their plane, these flatland creatures would see only cross-sections of three-dimensional reality, missing the full structure of objects that extend beyond their dimensional experience. If we are analogous to Abbott's Flatlanders, then our three-dimensional consciousness might perceive only cross-sections of higher dimensional reality. What we interpret as separate objects or events might be connected through extra-dimensional pathways invisible to our three-dimensional awareness, fundamentally altering our understanding of causality and identity. The hard problem of consciousness, explaining how subjective experience emerges from physical processes, becomes even more puzzling if consciousness operates through higher dimensional physics. Perhaps the qualitative aspects of experience that seem mysterious from a three-dimensional perspective become natural when viewed as higher dimensional phenomena. Some philosophers and scientists have speculated that consciousness might require higher dimensional information processing, capabilities that cannot be achieved through purely three-dimensional neural networks. If true, this would suggest deep connections between dimensional structure and the emergence of awareness. The nature of personal identity could be radically different if our existence extends into extra dimensions. What we consider to be individual selves might be three-dimensional cross-sections of higher dimensional beings, with our apparent separateness being an illusion created by dimensional limitations. Free will takes on new dimensions if human decision-making involves higher dimensional processes that are not fully determined by three-dimensional physical states. Extra dimensions might provide the additional degrees of freedom necessary for genuine agency and choice, resolving traditional debates about determinism and responsibility. The mind-body problem could find new solutions if consciousness operates through higher dimensional physics while the body remains primarily three-dimensional. This could explain how mental phenomena seem to transcend purely physical causation while remaining grounded in physical reality. Epistemological questions about the limits of knowledge become more complex if reality extends beyond our dimensional experience. How can three-dimensional beings acquire reliable knowledge about higher dimensional structure? What confidence can we have in scientific theories that attempt to describe dimensions we cannot directly experience? The relationship between mathematics and physical reality appears even more mysterious if mathematical structures describing higher dimensions correspond to actual spatial structure beyond our experience. This suggests that mathematical reasoning might provide access to aspects of reality transcending sensory experience. Dr. Max Tegmark's mathematical universe hypothesis proposes that reality is fundamentally mathematical, with consciousness emerging within mathematical structures. If true, this could explain why mathematical descriptions of higher dimensions feel natural and possibly correspond to actual dimensional structure. The anthropic principle takes on deeper significance if consciousness can only emerge within specific dimensional configurations. This would suggest that awareness plays a fundamental role in determining observable reality rather than being merely an accidental byproduct of complex physical processes. Religious and spiritual implications of extra dimensions have been explored by theologians and spiritual teachers who see higher dimensional physics as potentially validating concepts of transcendent reality beyond ordinary physical experience. Some traditions describe spiritual realms that might correspond to higher dimensional spaces. However, attempts to connect extra-dimensional physics with spiritual concepts must be approached carefully to avoid conflating scientific hypotheses with religious beliefs. Higher dimensional physics, if it exists, would be subject to natural laws and scientific investigation rather than transcending physical reality entirely. The problem of evil and suffering could be viewed differently if our three-dimensional experience represents only a limited perspective on higher dimensional reality. What appears tragic or meaningless from three-dimensional viewpoints might serve purposes visible only from higher dimensional perspectives. Ethical implications of extra-dimensional reality raise questions about moral responsibility and the scope of ethical consideration. If reality extends beyond three dimensions, do we have obligations regarding higher dimensional consequences of our actions? How should moral philosophy account for potentially hidden dimensions of existence? The concept of death could be fundamentally altered if consciousness involves higher dimensional structure that persists beyond the breakdown of three-dimensional biological systems. While purely speculative, this possibility suggests that extra-dimensional physics might eventually inform philosophical and religious questions about mortality and continuation of consciousness. Aesthetic experience and the nature of beauty might involve higher dimensional aspects of reality that we perceive only indirectly through three-dimensional representations. Mathematical beauty, artistic inspiration, and aesthetic appreciation might reflect awareness of higher dimensional harmonies and structures. The relationship between time and consciousness becomes more complex if extra dimensions include time-like dimensions or if higher dimensional structure affects the flow and perception of time. Our experience of temporal sequence might represent only one aspect of a richer higher dimensional temporal structure. Social and political philosophy must consider how extra-dimensional discoveries might affect human society, power structures, and concepts of equality and justice. If some individuals or groups gain access to higher dimensional capabilities, this could create unprecedented forms of inequality and social disruption. The meaning and purpose of human existence could be radically recontextualized if our three-dimensional experience represents only a small part of a much larger cosmic story unfolding in higher dimensions. This might provide new perspectives on questions about life's significance and humanity's place in the universe. Environmental ethics and our relationship with nature might need fundamental revision if ecosystems and natural processes involve higher dimensional structure that we are only beginning to understand. Our impact on three-dimensional environments might have higher dimensional consequences we cannot currently perceive. The possibility of contact with higher dimensional intelligence raises profound questions about communication, understanding, and coexistence with beings whose existence transcends our dimensional limitations. How could meaningful interaction occur between consciousness constrained to different dimensional structures? Scientific realism versus anti-realism debates become more complex when dealing with extra dimensions that cannot be directly observed. What does it mean to claim that higher dimensions are real if they forever remain beyond direct experience? How do we distinguish between useful mathematical models and actual dimensional structure? The relationship between objective reality and subjective experience might be mediated by dimensional structure in ways that affect fundamental philosophical questions about the nature of truth, knowledge, and existence. If consciousness involves higher dimensional processes, the distinction between objective and subjective might need reconceptualization. Cultural implications of extra-dimensional physics could be transformative as societies adapt to radically expanded concepts of spatial reality. Art, literature, religion, and popular culture would likely evolve new forms of expression that attempt to capture higher dimensional concepts and experiences. Educational philosophy would need to address how to prepare minds for understanding and potentially working with higher dimensional reality. This might require developing new forms of mathematical and spatial intuition that transcend current three-dimensional educational approaches. Perhaps most profoundly, extra-dimensional physics suggests that reality might be far stranger and more wonderful than our everyday experience suggests. If true, This would represent one of the most significant expansions of human perspective since the recognition that Earth is not the center of the cosmos. The humility required to acknowledge that our three-dimensional experience might represent only a tiny fraction of reality's full structure could fundamentally alter human attitudes toward knowledge, existence, and our place in what might be an unimaginably vast and complex higher-dimensional cosmos. As we approach our final exploration, we'll consider what the future might hold for understanding dimensional structure and whether humanity might eventually transcend current three-dimensional limitations to explore the full richness of spatial reality. Chapter 11. Future Discoveries. The future of dimensional physics stands poised at the threshold of discoveries that could fundamentally transform our understanding of space, reality, and the nature of existence itself, with theoretical breakthroughs, experimental innovations, and technological advances potentially revealing whether space truly contains more than three dimensions and whether humanity might someday transcend our current dimensional limitations. Theoretical advances in quantum gravity represent the most promising pathway toward understanding dimensional structure, as any complete theory unifying quantum mechanics and general relativity must explain why space-time has the dimensional configuration we observe rather than any of the other mathematically consistent possibilities. String theory continues evolving through new mathematical insights that might eventually predict the number of large spatial dimensions from first principles, rather than requiring anthropic selection or phenomenological input. Recent developments in string landscape studies, flux compactification, and duality relationships provide hope for eventually deriving dimensional structure from fundamental physics. Dr. Juan Aldesin's DCF-T correspondence has revealed unexpected connections between higher dimensional physics and lower dimensional field theories, suggesting that dimensional structure might be more flexible than previously thought. These holographic dualities might eventually explain how three-dimensional physics emerges from higher dimensional reality. Loop quantum gravity approaches space-time discretization from a fundamentally different perspective than string theory, potentially revealing how dimensional structure emerges from more basic quantum mechanical building blocks. The loop quantum gravity framework might predict specific dimensional configurations through its discrete geometric foundations. Emergent gravity theories propose that gravitational interactions and spacetime geometry arise from more fundamental quantum information processing systems. These approaches might explain dimensional structure through information-theoretic principles that determine optimal configurations for quantum information storage and processing. Experimental breakthroughs could come from several directions, including next-generation gravitational wave detectors that might reveal extra-dimensional signatures in gravitational radiation, ultra-high-energy particle accelerators that could produce evidence for higher-dimensional physics, or precision cosmological observations that constrain dimensional evolution. The planned Einstein Telescope and Cosmic Explorer gravitational wave observatories will achieve sensitivity levels that could detect extra-dimensional modifications to gravitational wave propagation, potentially revealing whether gravity truly propagates through additional spatial dimensions beyond the three we experience directly. Future particle accelerators, operating at much higher energies than current facilities, might reach energy scales where extra-dimensional effects become directly observable through particle production processes, missing energy signatures or modifications to fundamental force interactions. Quantum sensing technologies continue advancing towards sensitivity levels that might eventually detect extra-dimensional effects through precision measurements of fundamental constants, gravitational interactions, or quantum mechanical phenomena that could be modified by higher dimensional physics. Space-based experiments could test gravitational interactions over distance, ranges currently inaccessible from Earth's surface, potentially revealing extra-dimensional effects that operate at intermediate scales between laboratory measurements and cosmological observations. Advances in material science and nanotechnology might eventually enable construction of devices that interact with extra-dimensional structure if such dimensions exist at accessible scales. Metamaterials with carefully designed geometric properties could potentially probe or even manipulate extra-dimensional physics. Computational breakthroughs in simulating higher-dimensional physics could provide theoretical insights that guide experimental searches and help interpret observational data that might contain extra-dimensional signatures. Quantum computers might eventually enable simulations of higher-dimensional quantum systems. Artificial intelligence applications to dimensional physics could reveal patterns in theoretical models and experimental data that human researchers might miss, potentially identifying subtle signatures of extra-dimensional effects or suggesting new theoretical approaches to dimensional physics problems. Mathematical discoveries continue revealing new structures and relationships in higher-dimensional geometry that might correspond to actual physical reality. Pure mathematical research often predicts physical discoveries decades before experimental confirmation, suggesting that current mathematical advances might herald future dimensional physics breakthroughs. The development of new mathematical tools for understanding higher dimensional spaces, topological quantum field theories, and geometric analysis could provide the theoretical framework necessary for making specific predictions about dimensional structure that can be tested experimentally. Interdisciplinary approaches combining physics with neuroscience, computer science, and philosophy might reveal new perspectives on dimensional structure by exploring how consciousness, computation, and information processing relate to spatial geometry and physical law. Consciousness research might eventually reveal whether awareness involves higher dimensional information processing capabilities that transcend three-dimensional neural networks. Understanding the relationship between consciousness and dimensional structure could provide insights into both the nature of mind and the nature of space. If extra dimensions exist and become technologically accessible, the development of dimensional engineering could revolutionize human civilization through new forms of energy generation, communication, transportation, and manufacturing that transcend three-dimensional limitations. The possibility of controlled access to extra dimensions raises questions about human enhancement and the potential for expanding consciousness beyond current dimensional constraints. Future humans might develop capabilities that seem impossible from our current three-dimensional perspective. Educational systems would need fundamental restructuring to prepare future generations for understanding and working with higher dimensional physics. This might require developing new forms of mathematical intuition and spatial reasoning that transcend current three-dimensional educational approaches. Scientific methodology might need evolution to address the challenges of studying phenomena that cannot be directly observed or experienced. New epistemological frameworks could be necessary for understanding higher dimensional physics and distinguishing between mathematical models and physical reality. International cooperation will become increasingly important for dimensional physics research as experiments become more expensive and complex, while theoretical advances require collaboration across traditional disciplinary boundaries. Global coordination might be necessary for responsibly managing dimensional technologies if they become possible. The discovery of accessible extra dimensions could trigger scientific and technological revolutions comparable to quantum mechanics and relativity, with consequences for every aspect of human knowledge and capability. Such discoveries might fundamentally alter our concept of what it means to be human. Conversely, continued failure to find evidence for extra dimensions despite increasingly sensitive experiments might eventually rule out many theoretical proposals and force reconsideration of why three-dimensional space appears uniquely realized in nature. The resolution of dimensional physics questions might require entirely new theoretical frameworks that transcend current approaches like string theory and loop quantum gravity. Revolutionary discoveries often come from unexpected directions that weren't anticipated by existing research programs. Future discoveries might reveal that asking, "Why does space have 3 dimensions?" represents a category error based on incorrect assumptions about the nature of space, time, and physical reality. The true answer might require abandoning familiar concepts in favor of radically different perspectives. The timeline for major dimensional physics discoveries remains highly uncertain, potentially ranging from breakthrough discoveries within decades to fundamental insights that might require centuries of scientific development. The history of physics suggests that revolutionary discoveries often come when least expected. Ethical considerations will become increasingly important as dimensional physics research progresses, particularly if discoveries enable technologies with potential for significant social, environmental, or existential consequences. The responsible development of dimensional physics might require unprecedented global cooperation. Perhaps most importantly, future discoveries about dimensional structure could provide answers to some of humanity's deepest questions about the nature of reality, consciousness, and our place in what might be a vastly more complex and wonderful universe than our 3-dimensional experience suggests. The journey toward understanding dimensional structure represents more than scientific curiosity. It embodies humanity's drive to transcend current limitations and explore the full richness of reality. Whether space truly contains more than 3 dimensions, the search for answers pushes the boundaries of human knowledge and capability. The future of dimensional physics research will likely reveal whether our 3-dimensional world represents the full extent of spatial reality or merely the tiny fraction accessible to consciousness, constrained by evolutionary history and physical limitations. Either answer would profoundly impact our understanding of existence itself. As we conclude this exploration of dimensional physics, the question of why space has 3 dimensions remains open, inviting continued research that might eventually reveal whether humanity's future lies entirely within 3-dimensional constraints or extends into spatial realms currently beyond our imagination. Throughout this journey into the deepest mysteries of space itself, we've explored one of the most fundamental questions about reality. Why does our universe contain exactly 3 spatial dimensions instead of 2, 4, 5, or any other number from the infinite menu of mathematical possibilities? The answer touches every aspect of existence, from the stability of atoms to the possibility of consciousness itself. We began by recognizing that the 3-dimensional nature of space isn't just a mathematical detail. It's the fundamental framework that makes complexity possible. Every breath you take, every heartbeat, every thought depends on physics that works only because space has precisely 3 dimensions. The molecules reaching your lungs, the blood flowing through 3-dimensional vessels, and the neural networks processing these words all rely on 3-dimensional geometry. The physics in different dimensions reveal just how special 3-dimensional space truly is. In 2-dimensional space, atoms would collapse and complex chemistry would be impossible. Planetary orbits would be unstable, preventing the formation of solar systems that could support life over billions of years. In 4 or more dimensions, gravity and electromagnetism would behave so differently that stable matter might not exist at all. Through mathematical analysis, we discovered that while spaces with any number of dimensions are perfectly consistent from a mathematical perspective, they create universes where the delicate balance between forces that enables complexity would be completely disrupted. 3-dimensional space occupies a unique position where quantum mechanics, electromagnetism, and gravity interact in ways that allow atoms to form, planets to maintain stable orbits, and complex structures to persist over cosmic timescales. String theory opened our minds to the possibility that space might actually contain many more than 3 dimensions, perhaps 6 or 7. Additional spatial dimensions curled up so small that we cannot detect them directly. These extra dimensions might be real and present everywhere around us. yet hidden from our everyday experience by their microscopic size or exotic geometry. The stability requirements for complex structures showed us why 3 dimensions might be uniquely suited for the emergence of life and consciousness. Only in 3-dimensional space do we find the precise scaling relationships between surface area and volume, the specific geometric constraints on circulatory and nervous systems, and the mathematical properties that enable stable chemistry and information processing. The anthropic principle provided a different perspective. Perhaps we observe 3 spatial dimensions not because of fundamental physical laws, but because universes with other dimensional configurations cannot support observers capable of asking questions about dimensional structure. This reasoning suggests that consciousness itself might play a role in determining which dimensional configurations we can observe. Cosmological models revealed how dimensional structure might have been determined during the universe's earliest moments through phase transitions, symmetry breaking, and other dynamical processes. The number of large spatial dimensions might not be a fixed property of physical law, but rather the result of cosmic evolution during the first fraction of a second after the Big Bang. Experimental searches continue probing for evidence of extra dimensions through gravitational tests, particle accelerator experiments, and precision measurements of fundamental constants. While no definitive evidence has been found, these experiments continue constraining theoretical models and might eventually reveal hidden dimensional structure. The technological implications we explored could be revolutionary if extra dimensions exist and become accessible. New forms of energy generation, communication systems that transcend speed of light limitations, and transportation through higher dimensional shortcuts could transform human civilization in ways that currently seem like science fiction. Philosophically, the possibility of extra dimensions challenges our understanding of reality, consciousness, and existence itself. If space contains more dimensions than we can experience directly, our 3-dimensional perspective might represent only a tiny fraction of reality's full structure, fundamentally altering concepts of identity, causality, and the nature of awareness. Looking toward the future, we see theoretical and experimental advances that might eventually answer whether space truly has more than 3 dimensions and whether humanity might someday transcend current dimensional limitations. Quantum gravity theories, next-generation experiments, and new mathematical insights continue pushing toward resolution of these fundamental questions. As you go about your day after learning this, remember that every movement through space, every geometric relationship you perceive, and every physical interaction you experience depends on space having exactly 3 dimensions. The apparent simplicity of 3-dimensional geometry masks incredibly sophisticated physics that enables the emergence of complexity, consciousness, and the capacity to contemplate dimensional structure itself. When you reach for an object, navigate around obstacles, or observe the rich 3-dimensional world around you, consider that you're experiencing what might be the only dimensional configuration, compatible with complex structures and conscious observers. The 3-dimensional nature of space might represent one of the most profound fine-tuning examples in the universe. The question of why space has 3 dimensions connects to the deepest mysteries of existence. Why does anything exist instead of nothing? Why does the universe have the specific properties that enable complexity and consciousness to emerge? Why do we find ourselves in a cosmos where the fundamental structure of space itself seems precisely configured for the possibility of life and awareness? Understanding dimensional structure reveals that space isn't merely an empty stage where physical events occur, but rather a dynamical component of reality whose geometric properties determine what kinds of physics are possible. The dimensionality of space represents one of the most fundamental aspects of the universe's architecture. Perhaps most remarkably, the study of spatial dimensions shows that mathematics provides a window into the deepest aspects of reality. Mathematical structures describing higher dimensions might correspond to actual spatial structure beyond our direct experience, suggesting that pure mathematical reasoning can reveal truths about existence that transcend sensory experience. The three spatial dimensions we experience might represent either the full extent of spatial reality or merely the accessible portion of a much richer, higher dimensional cosmos. Either possibility would have profound implications for our understanding of physics, consciousness, and the nature of existence itself. If you made it this far, subscribe and give a thumbs up. Check out my video on how time could have more than one dimension. I'm sure you'll love exploring how temporal structure might be as complex and mysterious as spatial dimensionality. The reason space has three dimensions, whether determined by fundamental physics, cosmological evolution, or anthropic selection, ultimately enabled the emergence of observers capable of contemplating their own existence within the geometric framework that makes thought itself possible, creating one of the deepest and most beautiful connections between mathematics, physics, and consciousness in the known universe.